Hello, Flat Earth researchers, debaters and debunkers. I came across a short video clip recently that I thought would be a really good way to illustrate how we see a small local sun doing concentric circles to give us the seasons throughout the year above flat Earth. So we'll play the clip in a minute and then we'll come back and look at a couple of frames from that clip so you can see what I mean. This is showing trails created by an aircraft doing kind of elliptical or oblong paths in the sky, but it's a really good way to show this earth-bound perspective view of the sun if it were following these circles in the sky. And then we'll have a look at an animation that shows a top-down view of what we're talking about when we're referring to a local sun doing circles above flat Earth. First of all, though, disclaimer, this isn't to put across any particular flat Earth model. It's a way of illustrating an alternative way of seeing how the sun moves in the sky, rather than assuming that it's the globe Earth that is spinning to create day and night. So without further ado, let's have a look at that clip and we'll come back to it and show you these illustrations I've put together.
Друзья, кто подскажет, зачем самолет кружит над Новосибирском? Раз, два, три, четыре, пять, шесть кругов.
So to give us an earthbound perspective view of the sun doing a circular orbit above the level Earth, I've very crudely stitched together 3 frames from that video. And of course this is a very, very local view, and the actual path of the sun would be much larger and wider than this. But it gives you an idea of what we see happening from the Earth as the sun does a circuit and eventually goes off into the distance and sets beyond the horizon. But it doesn't actually go down underneath the Earth. It still remains in the sky. So following this particular trail on the outside, we can see that as the sun goes off into the distance following that trail, it would set beyond that building. All right. Of course, here it's going to come round again, but as I said, this is just a very crude representation. So we can see how that would make the sun reach its zenith in the sky. This would be midday for us, wherever we are, or whatever time of year it is. And then the sun would continue on its journey across from east to west. Okay, and then we could follow one of these smaller circles, and this would be at a different time of year when you've got obviously a different season going on, because you're not so close to the sun. And because it's not coming so close to you, the sun's elevation at its zenith, or your midday wherever you are, would be lower than it was when it was following this larger circle. So this simply shows how we would see the sun in different locations in the sky, or at different elevations in the sky, depending on the season. And that season depends on the size of the circle that the sun is doing above flat Earth. You can see here, if we follow one of these smaller circles, that even at midday the sun would be much further away, and so the elevation in the sky at its zenith would be much lower than any of these points. Yeah, it's really simple. Again, this is just very, very crude to illustrate what we see happening. And as the sun follows that circle, it sets, and we can just follow that circle around. You can see that square going around, hasn't gone below the Earth. It's not going all the way down underneath. It's just going to come up here and circle above us in the sky, east to west, and go off into the distance, remaining above the Earth, at the same height above the Earth, but we see the sun set because of our earthbound perspective. All right, so let's have a look at a bit more of a refined illustration like this. Here's another earthbound perspective view of what we would see happening in the sky if the sun was doing circular orbits above the level Earth. Obviously, in this case, we have to assume that we've got a very, very small level Earth. It's about the size of this city, just for the illustration purposes here. And so we have a very local sun with this red ellipse representing the circle that the sun does in the skies we saw from those top-down illustrations. Now again, it doesn't mean that that is exactly the so-called flat Earth model that I'm promoting here. You could have the sun doing circles or ellipses around the North Pole. You could have the same thing happening over the South Pole, if you like. But for showing how we see the sun in the sky, let's just use this illustration. And as we look at this one, we can see that the sun is at its zenith. It's at the highest point it will be in the sky, and it's quite a large circle. So it's going to be at a particular time of year, and this would maybe be the hottest time of year, some kind of summer. We have the sun at a very high elevation in the sky from our perspective here, and as it goes off to the east or west and goes around on its circular path. Remember that we're talking in terms of perspective here, the way we really see the world. So from this particular viewpoint, a circular orbit would appear to be elliptical. You'd only see a circle if you were looking straight on or directly at this circle or from the top down. But from this kind of sandwiched kind of view, we would have the sun appearing to make an elliptical circuit as it goes off there. So this would be a sunrise, as it were, and again we come back to midday. And of course, if it was really like this, it would remain light all day, and it may get slightly darker in the foreground as the sun goes off over here. You just wouldn't have so much light reaching us. So if it was a different season, let's say it's a colder time of year when the sun is doing a smaller circle, and we'll represent that with this orange circle here. So right now the sun would be off in the distance over the other parts of the city in the distance, and it comes around to us and we can see it coming across our portion of the sky from east to west and then reaching its zenith at midday. And here we see the sun at a lower elevation in the sky than it was in the summertime because it's further away, because the circle that the sun is doing is smaller. It's quite simple to understand, and it would make sense in terms of physics, in terms of the direct heat that you would experience depending on the size of these concentric circles throughout the year. All right? So, of course, again, this is a very, very local representation. Just have a look at the horizon here. You can see that it's quite clearly defined where the buildings are, but then we get this layer of, it could be smog, haze. It's just basically dense air. And so, ultimately, what happens at sunset is the sun gets cut off by this layer of air and even clouds above the surface that appear to be touching the surface because they are so far away. So the further away all that dense air becomes, the thinner and thinner it gets in our field of view, but it also becomes increasingly dense, and you know that you can see the sun go behind clouds and you are in shade once that happens. But of course that's not the case if you're somewhere else and that cloud isn't directly blocking the sun for you. So you can apply the same real world experiences to this scenario here. But let's just make that orbit a little bit larger. So as we are representing the laws of perspective that govern all of our observations on this two-dimensional image, we can't get exactly the effects that we see happening on the surface going on in the sky with this elliptical path here. What would happen as it got further away is that it would become more elongated. It would stretch down, follow a path that goes down towards the horizon more and eventually takes the sun beyond the horizon. So the easiest way to do that in this particular illustration, without wasting too much time, is to just bring this down, and we know then that what we see happening is further away from us because we've brought it lower down in our field of view. So actually this lower half of the ellipse would ideally be a bit higher and stretching off into the distance above the surface there, but it's good enough for our purposes here now. So let me just grab the sun and bring it down. So obviously the sun would often follow a path that's more like this. Okay, it's going up in an arc across the sky, but we'll just get it to follow this path for now. So it's risen in the east and it's arcing across the sky and going east to west, and then as it goes around on that second half of its circuit away from us, you can see that it's now gone beyond the horizon. It's not there anymore. Of course, it will get slightly lower because it's getting further away, and as I said, everything on or above the surface is contributing to blocking off the sun, but it's not going beneath our feet because we're on some imaginary globe. And as the sun comes round again, it rises in the east and comes up. So just think about this. It doesn't matter whether you consider the center to be the South Pole or the North Pole, or whether you consider yourself on the inside of one of these orbital circuits or on the outside. When the sun is at its zenith for your particular location, wherever you are, that is your local noon. And of course that will change if you just move down the road maybe 100 miles. Your local noon will be at a slightly different time, and it will only be when the sun is at its highest point in the sky, because that is when it is closest to you. So again, regardless of whether this circle, you're on the inside or the outside of this circle, you're only seeing half of it, and it's coming up from the horizon and going up into the sky because it's getting closer and closer to you. Let's just start it off over here in the east again, and it's getting closer and closer to you, and at midday or noon, that is the closest point, the highest point in the sky, and more directly overhead for you, or more towards directly overhead. And then as it continues on its circuit, it's going off into the distance. Again, remembering that this elliptical circuit will be more stretched out as it goes off into the distance, but you can see the effects there. Okay, and that's it. That's why perspective is the imaginary curve. You see how perspective, depending on our location, affects how we see things in the sky, whether it's the sun, the moon, or the stars. Polaris, for example, we know that the closer we are to something, the higher it is in the sky. So as far as latitudes go, which is the distance from the North Pole as you go towards the equator, the further away you got, if this was Polaris, then the lower down in the sky it would appear to be. And that would give you your latitude. The latitudes on the Earth are the same as the angle at which we see the sun when we, Polaris, when we take a reading. And so we can do the same with the sun. Your location, whether it's on the equator or north or south of the equator will dictate the height at which you see the sun, or the angle of elevation, or the attitude of the sun, the altitude, sorry, of the sun in your local view. And the highest point the sun reaches in the sky is your local noon, and that's when the sun is closest to you. And from then on, it gets further and further away from you until it is simply obscured by the horizon. Remember that the horizon becomes a thin line, but it's still a lot of height of air, dense air and vapor and everything else, and clouds as well, that obstruct your view. All right? It's really that simple. So we can use the geometry of perspective to describe exactly what we're seeing on a level Earth. And that's why perspective is the imaginary curve. There is no curve on the surface of the Earth. It is this arc of curvature that we see in the sky due to perspective when looking at objects in the sky that gives us this impression of some kind of dome-like effect, a dome of perspective in which we see the sun get closer to us and then further away. Same for the moon. Thank you very much.